I don't see people. Okay. Thanks for the organizer to give me the opportunity to have this talk here. So again, I will talk about this single pulse Wollaston polarimeter for magnetodynamical studies. So my presentation will be, let's say, on the technical side. I'm an experimentalist, so I will just quickly, give a review on femtomagnetism, then talk about resonant magneto-optical effect, review a little bit the X-ray polarimeters that are available today. Then I will talk about our design. It's called Tonix, and then I will show like few our experimental results on the demagnetization of permalloy and on the nickel to silicon spin injection. So I will go very quickly because there is no need. So everything started in 1996 with the demagnetization of ferromagnetic nickel observed by time-resolved magneto-optical effect. So you all know what you do. You have a very short pulse, excite the system, and what you observe, you have a drop of the magnetization. People expected that the magnetization would be decreasing slowly because they thought that you hit electrons, then you go to the phonons, and only later you hit up the spin system again. But it was very fast instead. So people thought like, okay, there is opportunity of more studies, let's say something that theory does not predict. And I would say that 10 years later, there was this all optical magnetic recorded, my linear and circular pump pulses. And it's very nice described in this slide. So what you have a magnetic system with two opposite magnetization, and you scan the system with the right circular polarized pulse, and you flip the wrong domain in a certain sense, and with the opposite polarization, you, let's say, flip the other domain. So there was very interesting result. And again, a few years later, there was a description of what happens. You have an ultrafast momentum transfer, thereby time-resolved resonant X-ray magnetic scattering at femtosecond sources. So what they discovered was that this is a gadolinium iron cobalt, is a ferrimagnet. They found out that the magnetization iron was faster than gadolinium, and this was due to spin transfer. So I focus on, because I'm an experimental scientist, on the technique. So this was a very advanced experiment performed at a free electron laser and gave very good insight on this physics. And I want to also mention this very important, let's say, phenomenon that was proposed in those days. So for instance, it is super diffusive currents. And in this article, they were discussing the fact that it's possibly the ultrafast spin transport was the key to femtosecond demagnetization. I would say that super diffusive currents are debated right now. So they had, let's say, there is a long debate. They made some mistake in the calculation of the of the absorption profile. There is a lot of discussion ongoing, but I would say that super diffusive currents, they definitely stimulated, I believe, the field of femtomagnetic research, and they end up to have, let's say, nice demonstration of application with the terahertz emitters that we also have seen some talks. But what I would like to underline here and is the fact that there was a need in previous 10 years of element and depth sensitive probe of magnetization. And as you see here, you have a system stack, and you would like to know what happens to the magnetization in every layer and even to be element sensitive. So how to gain depth sensitivity? So I would say that this is not only my point of view, that I hope actually that researchers are interested in this aspect. In fact, I would say a lot of experimental scientists are trying to get techniques that measure the profile of the magnetization. And I will underline this by showing that, for instance, very recent new setup was developed exploiting X-ray magnetic profiling by transverse Moche as a function of the angle. So what you do, you scan theta and you measure the reflectivity. You have an applied field perpendicular to the optical plane. You measure the reflectivity as a function of angle at the two fields, so field up and down, and you measure the symmetry, and you can reconstruct the exact magnetization profile in the system. So just to show that indeed there is the community of HIG sources, free electron laser, we are trying to get into this direction. And I'm not the only one, I would say. So also there is another work. If you see here, they exploit exactly the same phenomenon. And they just use a different plasma source that generates up to 1,500 electron volt. And again, another setup rising, trying to exploit a HGZ source. But again, let's say, the idea is that we want to learn more about what happens in each layer. And so for instance, here they want to investigate this chromium iron stack. And so Transer-Moke exploits resonant magneto-optical Kerr effect. So I want to quickly describe what resonant Moke is. I think it's a new ultrafast element-specific probe of magnetization. It's not my opinion, but let's say I will show you the first authors that claim this. So resonant Moke is a magneto-optical Kerr effect performed at photon energies that coincide with an X-ray absorption edge in one of the constituent elements in the sample. So what is a Moke experiment? It's like as follows. So you have a green magnetized sample. You apply a field. You magnetize the system in this direction, so in the scattering plane. You come with linearly polarized light. And what you observe is that because of the magnetization, you have a rotation of the polarization. If you flip the magnetization, the polarization changes. So that's just magneto-optical Kerr effect, and you do it in the X-rays. And there are several advantages of doing this experiment that was very important to develop the field of femtomagnetization, but now we turn it into X-rays. So you can use linear polarization that is easier to control. You can perform the experiment at M edges, so that are in the EUV range, so quite accessible. The effect is large. I will have a slide, very large with respect to visible in particular. And you work in reflection from bulk system, which is this actually, if you compare with the reflectivity of hard X-rays, then when the reflectivity drops. Okay, and you still have element sensitivity. So this first experiment, these are the claim of this group, Japanese group. And they'll be showing that indeed, you can measure nickel, for instance, and you see that the Kerr rotation in the EUV range are huge on the 10-degree level. And okay, so your problem is only, okay, how do I measure polarization changes in the X-ray? Well, it's a little bit more complicated than in the visible. So this is one design. It's called Rabinovich, or rotating analyzing element, and it is very simple. The idea is that you have, let's say, unknown incoming electric field. You rotate your mirror plus detector around this K axis or chi here. And what you have, because RS and RP are different values, right? You are almost at the Brewster angle, so the reflectivity with respect to, let's say, when the polarization of light is perpendicular, so S to the optical plane, with respect to P are very different. So when what you reconstruct, it's the intensity as a function of the angle, that goes, let's say, follows a sine square wave. The minimum corresponds to the position where your light is, let's say, is either orthogonal or parallel. And when you apply field, you just measure a complete shift of this curve. So that's what they were showing was, I would say, very interesting. And this detector is quite efficient because you can use a multi-layer. And, but you need to make a full rotation of the detector, and you need an I0, okay? So there was another design, actually investigated also at Fermi, where I work, and Matteo is actually in the audience here somewhere. And this is the compact polarimeter based on two conical mirrors for XUV light. So it's based on the same physics, so Brewster angle. The idea, you come with the polarization, and when the light is, let's say, reflected by these two surfaces, because light is with the electric vector pointing out of the presentation board, you get S polarization, so it's let's say, strongly reflected. When instead you come on this surface, it's P, so it's 0, so you have this ring with the cut. And when the electric field changes, this ring is rotating, so you can reconstruct. So there are several advantages. You don't need I0. You can have a full polarization, because if it's nicely circular without cut, it's circular, polarized light, and you need no adjustment after preliminary alignment. In principle, the disadvantage, in my opinion, that you have two reflections, so the reflectivity drops, and at best you have 6% if you would actually be able to make multi-layer with these conical surfaces. And, but let's go to our design. So I wanted to reproduce the Wollaston polarizer in the visible. So this is the Wollaston polarizer in the UV X-ray range. So what we wanted, because we wanted to make a good measurement very fast, is that it could be able to reconstruct the angle of the polarization in a single shot, to be very efficient, to be able to work with the pulses just reflected from a surface. So that's important, because I believe that growing good samples is very important for the community. And no moving mechanical parts and no I0. So that was our final design. It's very simple. You have a mirror that cuts the beam in two, first mirror, and reflects the light into this detector. The leftover beam goes to the second mirror and reflects on the second MCP. The idea is that if you come with the horizontal X-ray pulse, and let's say it turns to 45 degrees, the idea is that you are in this, for this reflection, it's a P reflection, so it's 0. You don't get any intensity on this detector. And for this, let's say, optical plane, you are S, so it's intense. So the difference of the two is just proportional to the polarization. So why do you want to do these experiments? MOCE in the X-ray regime. Why won't you complicate your life with the X-ray polarimeters, essentially? So I want just to give an idea. So this is a longitudinal MOCE, so you can do in the visible. In the X-ray, doesn't matter. The mathematics is the same. You have a dielectric tensor, and you have these off-diagonal terms. You know them from literature, and you can calculate the K-rotation and K-ellipticity. So ellipticity is because technically the polarization is slightly circular. So you take the data from literature. You have a refractive index for cobalt, for instance, in the visible and in the EUV range, so where the M edges, M to 3 edges lay. Okay, these are just the number. You can do nothing with that. That's, let's say, nature. Q, it's nice to see that, okay, N is quite different, while Q, it's pretty much on the same range. The penetration depth at this color, it's pretty much the same, okay? But if you measure the compare, for instance, this is the K-rotation as a function of the angle of incidence. For the visible range, you reach a maximum, let's say, around 2 milliradians, while for the, in the UV range, this blows up to 180 milliradians, so that is 10 degrees. So it's really a good, very easy to measure, let's say, in principle. And, okay, I plot also the reflectivity. Okay, for the disadvantage is that this is on the 0.2%, 0.02% range for the UV. Not as bad as, let's say, what happens in the hard X-ray regime. And here I wanted to, I made a calculation just to give you an idea that if you would have a monolayer of cobalt on copper, in the visible range, you would go to milliradians, changes of rotation, so very little. And in the EUV range, you still have a large rotation that you can measure. So in principle, this technique, this defect, it should be easy to measure for very thin layers, for very, let's say, possibly magnetic defects on surfaces, stuff like this. Okay, so the tonic is installed at Magnetism, that is at Fermi, that is at Elettra, that is in Trieste, in Italy, just to, don't know if, just to be sure, let's say. I want to make a little bit of publicity about Fermi as well, so, but there was a Laura already, so I just want to underline once more. So that's Magnetism, the beamline where I work. So this is how is it installed. We have a relatively good pressure. In vacuum transfer, so if you have air-sensitive system, we can make effort to not destroy them. 1.6 Tesla, 20 Kelvin facility. We have lots of laser options. This, for instance, is just to show that we can take some simple experiment with, let's say, fundamental, 800 nanometers, second harmonic, third harmonic. Soon we will have 50 femtosecond pump pulse. And we have also OPA and DFG sources, so to the, let's say, micron range. So for more details, please go to Marco. The poster actually was a few days ago, so you cannot see, but you can ask him to, he's the boss, but you can still ask him to show the presentation again, I believe. So that's the first test on our polarimeter, on this permalloy, nickel-iron permalloy. So we used, again, the standard configuration, longitudinal MOCA, you pump at very narrow angles, and you probe the rotation. So we get stuff like this. So you measure at two edges, like iron and nickel. So you can measure reconstruct several things. You can measure the reflectivity changes, just to see, let's say, the dynamics of charges and phonons and heat. And you can reconstruct the absolute magnetization changes of the two species. And of course, also, you can change the magnetization and measure the magnetization as a function of field. Here, the curves look different just because of sampling, just to avoid some question. So again, we have the expert on this, and this is our postdoc, Risa, and you can, again, this poster was a few days ago, so, but you can still discuss with her about this data. What I want to discuss is our, let's say, one of our test experiment. It was a proposal quite long ago, but because of COVID, there was a long delay, etc. But it's our business, they say. So we wanted to investigate nickel to silicon spin injection by the super diffusive currents. So in the 2016, Marco Battiato was proposing the spin injection from nickel to silicon. He predicted it to be chargeless. That means independent from the charge carrier flow. 80% spin polarized and ultra short as a ballistic spin soliton that is 100 femtosecond short. I like, actually, he was coming with these funny change of metrics showing that this ballistic spin current was very fast, so traveling at 1 nanometer per femtosecond. So it's nice because for people that work in femtosecond field, they get a very clear idea immediately. So we said, okay, we test this idea. So we find the people to make a very good sample. We deposited nickel on silicon, but actually we included a very thin layer of silicon nitride to avoid mixing. And then we said, okay, we pump with this infrared laser that happens to be absorbed completely by the nickel, okay, 95%. Then we probe at the L23 edge in silicon, which is actually the only edge you can measure. So at under 2 electron volt, and the idea is you measure the magnetization of silicon, and at 77 eV, you measure only the magnetization on nickel. So the setup is our standard setup, so you don't have to change anything. The advantage is, again, I think that the system could be grown very carefully. Again, working in reflection allows you to not to work with the very films on membranes, for instance. So this is our main results. So I will take some time to describe this. So the red curves are the data measured at the nickel edge, and the blue data are the data measured at the silicon edge. So what happens? Let's say we look at the empty curves in nickel. So before the pump arrival, you have a certain magnetization, and after the pump, so it's 500 femtosecond after the pump arrival, you have a drop of magnetization. And if you see on the figure C, you have its time scale. So this magnetization drops of half its amount in 100 femtosecond, let's say. So we expected, so we wanted to see the spin injection. So there is no current flow. In principle, we don't apply any bias. We expected that to measure at the silicon edge, no magnetization at the beginning, and we would induce an increase of magnetization with the pump. But instead, we observed something, let's say, different. And as you see here, something similar to the nickel. So the silicon was already magnetized before the pump arrival and had a drop soon after the pump arrival. So we were quite surprised about this. We thought that maybe there was some, let's say, problem on our detection, but actually, if you measure the time scale, they are different. So if there was some artifact, you would see the same, let's say, time scale as well. So we clearly have a difference in rise time. And we believe that this difference is due to possibly, let's say, the spin injection. And let me quickly go to the explanation. So let's look at the curve on the top. So above this dotted line. So this is what happens, how the system is before you pump arrival. So you have a magnetization on this nickel because it's a ferromagnetic. We do the experiment at room temperature. But your silicon is already magnetic. And there are several mechanisms that can cause this magnetization. For instance, one thing that can, of course, I think is mixing. But we know that mixing of silicon and nickel, but we know that nickel silicides are actually not magnetic. So instead, we observe a ferromagnetic ordering of silicon. So we are actually investigating the mechanisms. So what happens when you pump the system? You have a very quick drop of the nickel magnetization. That is very long, not surprising. It is followed, and we believe that it is followed by very quickly by the magnetization in silicon, because they are coupled. But at the same time, part of the spin are injected as predicted by Battiato, and is depicted by this black curve, black Gaussian pulse, into the silicon at very fast time scale, so that to affect the decrease of the magnetization in silicon that was there already competes with the injection of carriers. So that's why you have this slowdown of the transient curve. But there was a poster, and we are, if you want more details about this, you can stop this, our PhD, Simone Laterza, that is also at the conference today. So we'll conclude. So the advantages of our polarimeter is that you can work with a single pass. It works in reflection. We tested already several edges, so we believe that we can measure, well, let's say, quite a few elements of the periodic table. And we also worked with antiferromagnetic samples. Unfortunately, the data are not mine, so I cannot show anything. So, and about resonant Moche is a huge signal, and I believe that we, in the future, we could measure ultra-thin layers or even single magnetic molecules or magnetic defects on surfaces. So maybe a perspective. And I want to conclude. Just, I think the take-home message that I would like to deliver is that, so there are several experimentalists like me that we are trying hard to perform detailed and better experiments. And we think that the community needs, for instance, as you see, I'm not the only one. There are people that are working to develop this system. It's tough. It takes time, money, and the idea is that to measure the magnetization profile and be element sensitive. But are we going in the right direction? But this is an open question, of course, because in a very long time scale. Because yeah, that's it. I hope that should be okay. There is a lot of people already. I thought this system was very simple. A lot of people had to work to make this working. And I would like to thank you for your attention. And there is an open position for PhD. So contact me and Marco, please, if you're interested. And that's it. So this is our Trieste landscape. Yeah, thank you.